In this video, I'm going to show you how to derive the equations of motion for a double pendulum using the Lagrangian. Well, what is the Lagrangian? It's right here, written with the script L, T minus U. That is simply the kinetic energy minus the potential energy. So this is a really powerful technique because all we have to do is be able to write the kinetic energy and the potential energy in terms of generalized coordinates, and then we can get the equations of motion. So I'm going to show you how to do that. So first we have two different masses. They're both of equal mass, and two different lines, both of length L. So if we want to write this in a generalized coordinate, we would draw a little vertical line here and define an angle measured that direction called theta 1. And for the second mass, we would draw a vertical line here and define another angle called theta 2. Since the lengths L are both fixed, we can unambiguously describe the position of both masses in terms of these coordinates theta. These are our generalized coordinates. So now the next step is to construct the Lagrangian. And to do that, we need to be able to write the kinetic energy. We'll start with the kinetic energy. So, the way that we would go about this, say that T equals 1/2 m times the velocity of that m squared, right? So since these are fixed lengths, they're moving in circular motion, right? So for this first mass, we would have 1/2 m, then since it's circular motion, the velocity would be L theta 1 dot whole quantity squared, right? Because if you remember, if you have something moving in a circular path, the linear velocity is equal to the radius of that circle times the angular frequency, right? So theta 1 dot, this is the time derivative of theta. This is our angular velocity. So then for the next one, we'd have 1/2 m L. Oh, sorry, I made a mistake here. This is the most important part. So the second mass is moving, our coordinate is defined with respect to the first mass. So our velocity needs to be the sum of the two velocities, right? If that doesn't make any sense, hopefully it will in a second here. So this is going to be L theta 1 dot, right? That's the velocity of the first mass, plus L theta 2 dot. And then this whole quantity needs to be squared, because theta 1 dot, or mass 1, is going to be moving with some velocity, and then mass 2 is going to be moving with some velocity relative to mass 1. And we need to write the inertial velocity. So with respect to a fixed reference frame, that's the velocity that we're writing here. This is the velocity of mass 1 plus the velocity of mass 2 relative to mass 1. So then that gives us the inertial velocity of mass 2. So then we can move on here to potential energy, which, as you can see, the traditional way to write this, since gravity is acting downward, it would just be mg y, where y would be some vertical coordinate. But we're writing this in terms of theta. So if we want to get a vertical displacement for this mass 1 right here, we could draw a right triangle here, just a projection, and we can see that we can write the height of mass 1 at any point. It's just given by the length of this leg here, drawn in red. So as you can see from here, this length right here, this is just L cosine theta 1, right? And we can do the exact same treatment for our second mass. This height is this little displacement vector here. This is just L cosine theta 2. So something that I find particularly tricky with this, or at least I did it first, is getting the sign right on the potential energy. So the way that I go thinking about this is, if my generalized coordinate gets larger, am I going to a higher potential energy or a lower potential energy? If my potential energy gets larger as my coordinate gets larger, then it's a positive sign, right? If it's the other way around, then you need a negative sign. Okay, so since if theta gets bigger, the cosine of theta gets smaller, right? So if the cosine of theta gets smaller, we're actually moving to a higher elevation. If that makes sense, if you can see that. Well, probably a better way to do this is if we say that theta gets smaller, or if theta gets smaller, the cosine of theta is going to get larger. And that's moving to a lower height, so it'll be a lower potential energy. So as theta gets smaller, the height gets smaller. So we can have a positive sign as theta gets larger, we're moving to a higher potential energy. So we do not need a minus sign in our potential energy equation. So our potential energy equation is just the sum of the potential energies of the two masses. So for the first mass, that's just going to be mgl cos theta 1. And then for our second mass, it's going to be, remember we have to sum these together for the potential energy of the second mass. So it'll be mgl cos theta 1 plus L cosine theta 2. So now we have our kinetic energy and our potential energy, and we can construct our Lagrangian from this. So just to remind you, we'll zoom back out. The Lagrangian is a kinetic energy minus the potential energy. So we can simply write that, substituting in. And then I'm going to go ahead and multiply this out, just because it'll make it easier for taking our derivatives. We'll get L squared theta 1 dot squared plus 2 L squared theta 1 dot theta 2 dot plus L squared theta 2 dot squared. So there's our kinetic energy, and we need to subtract off the potential energy. Get minus mg L cosine theta 1 minus mg L cosine theta 1 minus mg L cosine theta 2. I just distributed that out. So now we have our completed Lagrangian, and from here we need to get the equations of motion. The way that you do this is use the Euler-Lagrange equation. I'll show you what that is in a general sense. So what that is we say that the partial derivative of the Lagrangian with respect to our ith generalized coordinate minus the time derivative of the partial derivative with respect to our ith generalized coordinates time derivative is equal to 0. What this is doing is finding the stationary points of the action functional. I'm not going to go into that in this video. It's kind of complicated, but this is what you need to solve it. So since we have two masses and they're obviously coupled together, we should expect two coupled differential equations at the end. So let's go ahead and do that. So we need to find the partial derivative of the Lagrangian with respect to theta 1 first. So we can do that. Just look here. So we're differentiating with respect to theta 1. We're not differentiating with respect to theta 1 dot. So this first term here goes to 0 in the derivative. This goes to 0. This goes to 0. This goes to 0. So here we have a theta 1 term. So need to take a derivative of that. If we take the derivative of cosine theta is minus the sine theta. So we have, let me change color. Mg sine theta 1, and we need an L. Here's another one of those, so that's just going to be 2. And that's it for that part. And then we will need to take the time derivative of, I'm going to go ahead and take the partial derivative of the Lagrangian. Well, let me back up. We'll do this one at a time. So the partial derivative of the Lagrangian with respect to theta 1 dot. That's what we need to find now. So this first term here, just take a normal derivative. And for the second part here, we have m L squared theta 1 dot plus m L squared theta 2 dot. That's from this middle term here. And the third term in parentheses there has no dependence on theta 1 dot, so we don't have to worry about that. And neither does anything else in this equation. So now we need to take the time derivative of this. So that's pretty simple here. We just have ml squared theta 1 double dot plus, well, let me just go ahead and combine those. Two ml squared theta 1 double dot plus ml squared theta 2 double dot. And then based on this equation right here, we just set these two things equal to each other. So we have 2mgl sine theta 1 equals 2ml squared theta 1 double dot plus ml squared theta 2 double dot. So now we need to do the same exact thing for the other coordinate. So we'll just start off, take the partial derivative of the Lagrangian with respect to theta 2, wherever I wrote the Lagrangian here. So as you can see, none of these dot terms have any dependence on theta 2, and there's only one term that does. So this is just going to become mgl sine theta 2. So now we need to take the partial derivative of the Lagrangian with respect to theta 2 dot. So this will just be ml squared theta 1 dot plus ml squared theta 2 dot from that middle term. And now we need to take the time derivative of this. It's pretty simple. Theta, or single dots just become double dots because there's no other time dependence in here. And then we can equate these two equations. So we have mgl sine theta 2 is equal to ml squared theta 1 double dot plus ml squared theta 2 double dot. And then our other equation, I'll just rewrite it here. 2mgl sine theta 1, is equal to 2ml squared theta 1 double dot plus ml squared theta 2 double dot.